Okay, there we go. Hopefully this all works. My PowerPoint and Zoom have stopped getting along with each other. Even a reboot here hasn't solved that. So welcome everybody. Thank you for joining us. This is our Wi-Fi 101 webinar. So what we're going to go through today, we're going to talk a little bit about Wi-Fi, how it works, some of the technologies involved. Towards the end, we will talk a little bit about Wi-Fi 6 and some key important things to know about Wi-Fi 6. We also will be doing another Wi-Fi 6 dedicated webinar where we go more in depth into Wi-Fi 6 here in the upcoming future. So first off, let's do me a favor here. If you are hearing my voice, go ahead and raise your hand. Okay, we've got hands being raised, so at least some of you can hear me. So it looks like we're going here. So as we go through today, use the Q&A box to send in any questions as we go through, and I'll do my best to answer them. I'll try to do it as we go through today, but some questions we may need to wait till the end before I can answer them. But again, use the Q&A. Don't raise your hand. Don't send it via chat. Q&A is what's up on my screen that I can see while doing today's presentation. So for those of you not familiar with Zycel, we'll do one slide here, a little bit on our background. Zycel has been around since 1989 making computer networking equipment. So we've been doing this for a long time. For a while there, we were even making our own Wi-Fi chips and developing some new technologies that ended up being used as part of some of the Wi-Fi standards that are around today. We operate in 150 different global markets. We've got a little over 100 million devices deployed out in the field. Our US office is based out of Anaheim, California. So that is sales, marketing, that is our warehouse, and it is also where tech support is done. So when you call in, you do talk to a Zycel employee, usually working out of the Anaheim office, although these days there's a good chance you're going to get somebody at least during normal business hours. I think right now we've got it set up so if you call in after hours, you get transferred to, I think, our European tech support office. But during business hours, you're talking to somebody here in Anaheim. Okay, that's it for a background on us. Now let's start talking about Wi-Fi. So there's a couple different players here when it comes to Wi-Fi. There's the IEEE, the Wi-Fi Alliance, and the FCC, and people tend to get these a little mixed up. All three of these help contribute to Wi-Fi as it is today. We'll start with the FCC. That's the big dog there, right? The federal government. These set the rules as far as what sort of radio frequencies can be used, the rules you have to follow when using those radio frequencies, power output, things like that. There is IEEE. So the IEEE group is an industry group where engineers get together and create all the standards that make networking work. So just about anything networking related is going to be based on IEEE standard. That's where we get 802.11 from, because Wi-Fi is defined by the 802.11 family of specifications. And then there is the Wi-Fi Alliance. So the Wi-Fi Alliance is a group of manufacturers that get together. Their main goal, at least in the early days, was to help deal with incompatibility. So even though everyone was following the IEEE standards, when it comes to things in words, a lot of it's open to interpretation. Things don't get defined as exact as maybe needed. So when there's some fudge room there, some manufacturers were doing it one way, some manufacturers were doing it another way, and it was causing compatibility issues. So the Wi-Fi Alliance was formed and stepped up to help solve those compatibility issues and do compatibility testing. These days, you mostly see Wi-Fi certified on consumer products. You don't normally see it on the business products that much. Um, it's more there for consumers to feel peace of mind when buying a piece of consumer equipment that's going to work. The Wi-Fi Alliance over the years has become more of a marketing company. They're the ones that have decided to rebrand all the Wi-Fi technologies as Wi-Fi 1 through 6 at the moment, instead of going with 11A, 11B, etc. So Wi-Fi works using radio waves, right? So these are anything that's using radio waves, whether we're talking a remote control car or we're talking TVs, is using radio waves to transmit data. So some general rules here, basically, as frequency goes up, the easier it is to frame data on that. So as frequency goes up, more data generally can be put on there. But also as frequency goes up, the range gets reduced. So a good example of both of these here would be new 5G for cell phones, right? So 5G for cell phones, speeds are all over the place, right? So Verizon advertises just ridiculously fast speeds. And the reason they can do that is because they're using something called millimeter wave, which which is in the 60 gigahertz spectrum. So again, frequency goes up, you can cram a lot of data there, which is why Verizon gets to advertise faster speeds than, say, T-Mobile, who is using stuff at the lower end of the frequency range for doing their 5G. I think they get as low as maybe 600 megahertz for some of their 5G deployments. Maybe wrong on that, but that's why you're seeing different speeds. But also, an important thing here is to get those Verizon high speeds, because it's 60 gigahertz, that signal can't really pass through anything. So you need to be almost line of sight to the tower to be able to connect and get those speeds. So it really doesn't work when you're indoors, and even when you're outdoors. You know, if there's trees in the way or any sort of obstructions, it degrades and may completely block that 60 gigahertz signal. Same thing you might have experienced with cell phones, or not cell phones, excuse me, cordless phones when you were younger. At least for those of us that are old enough to have lived through the progression, the original cordless phones used 900 megahertz. You had really fantastic range. I remember being able to walk across the street to my friend's house and be able to maintain a phone call. And then we moved from 900 megahertz to 2.4 because 900 was too crowded. There was interference between, because everyone now had this cordless phone. So we moved to 2.4. It opened up more spectrum so you can have more simultaneous calls. Yeah, going at the same time, really important if you lived in or near a condo or apartment building. And the sound quality got better, right? Because higher frequency, more data, so you could get better sound quality. And then we moved from 2.4 to 5. And you notice the same thing. Sound quality got better, but the range reduced. So, and you'll also notice there when we're talking about this, that 2.4 and 5, which were used by cordless phones, are also the same area of spectrum that's being used by Wi-Fi. So the reason for that is because the FCC has designated only small amounts of bandwidth that are able to be used by everybody without a license. Generally, if you want to try to broadcast something with a radio tower or radio device, you need to get a license from the FCC. Buy a spectrum, you need to verify you're following all these different rules. But the FCC has opened up these other little chunks of spectrum that basically anybody can use with some very basic licenses required. So that's where everything is, 900 megahertz, 2.45. So 900 megahertz, too small, too low of a frequency, so it was never used for Wi-Fi, but these days everything is either 2.4 or 5. So you'll see a lot of consumer equipment out there. Consumer equipment, if they're talking about the power output, usually talks about milliwatts or watts of power. But when you're looking at business products, data sheets will usually. The DBM is a little bit better way of doing things simply because, okay, I'm going to complain about my audio. Let me adjust my mic. Not as close as I can get it. So hopefully that's better. If not, I'm not sure what's going on. It's a USB connection. Hopefully this is better, guys. If not, I don't know what else I could do. So anyway, DBM is nice because when you're calculating links and things like that, you can easily calculate the total EIRP just by taking a look at the power output from the chip, adding in any antenna gain you get, which is measured in dBi, and subtracting any loss based on cable length or connectors. So it's really easy to calculate and add things together because you can simply add it. Whereas you can't add milliwatts to dBi to figure that stuff out. As a general rule, my mouth is hitting the mic now, so let me a little bit. Every 3 dB gain is basically a doubling of the milliwatt output power. So going from 20 dB to 23 dB takes your power output from 100 milliwatts to 200 milliwatts. This is also just from just trying to eyeball range and how much you're going to increase coverage. DBM is much closer to what you're going to experience in the real world, which is milliwatts, right? So if you go from 100 to 200 milliwatts, a common complaint we get on the consumer side of things is, well, wait a minute, my range didn't double. I doubled my power, I didn't double my range. So looking at just milliwatts itself can be kind of misleading as to what sort of range you can get. And we'll talk a little bit more about how range works and stuff like that, and some of the other issues that cause issues with range. Something that tends to get overlooked a lot is the signal to noise ratio. This is actually what's going to determine most of the time the quality of the Wi-Fi connection. Sorry, I'm messing with the mic. So when you're connected, this is what's going to determine basically what data rate you're connecting at. People tend to overlook this. So this is basically measuring the strength of the signal that you're transmitting your Wi-Fi to any sort of noise that's coming in. So it might be interference from your neighbor's Wi-Fi, Wi-Fi in the next building, other 2.4 or 5 gigahertz devices that you are using. Um, so a good example of this would be simply talking to somebody, right? If me and you are sitting alone in a conference room next to each other, you don't have to speak very loudly because there's almost no noise, right? There's no other background noise. But you try to have that same conversation in a crowded bar, you're not going to be able to hear each other without shouting louder and raising your voice. Why? Because the noise of everyone else talking, whatever else is going on, that's your noise. So you have to raise your signal to get above that. So it's the same thing with Wi-Fi. And then attenuation plays a big deal as far as range and things do with Wi-Fi. So attenuation is basically just how much the signal is degrading. So as the signal travels through the air, it degrades. As it travels through the wall, it degrades even more. So based on what the substance is affects how much the signal is going to degrade. So here we've got this little chart. We'll start here at the bottom. And this is just showing how much loss or attenuation you might experience some of these different mediums. So right, a window, standard window is going to get you up to 3 dB. A tinted window on something that's got like a metal coating to keep the UV out or the infrared out, it may get you up to almost 9 dB of loss. So again, every 3 dB is doubling, or in this case, halving of the milliwatt output. So you can see how something here like a solid core wall can make a huge difference as far as how far that signal goes. So if you really want to know how far your signal is going to go, here is the formula right here. This is your free space, so assuming just plain air path loss. So you've got 20 log 10 of your distance plus 20 log 10 of the frequency plus 92.45. That's how you can figure out how far your signal is going to go. And if you actually do decide to punch this in and calculate it, you might be surprised just how far even a low power output 2.4 device can go. Just a typical 20 dBm home router can go, I believe, over a mile as far as that signal goes, assuming no obstructions and no other noise. So Wi-Fi range is a combination of a lot of different things. There's your signal strength, there's that signal to noise ratio we were talking about earlier, the attenuation, and the frequency being used, right? So there's all these different things that go into determining how far the signal is going to go. So this is a problem we run into a lot where people, tell me what your coverage is of your access point. Well, it really, really is affected by where you've deployed the device and what else is going on in the environment. If it's really humid where you're using this, the range will be less than in an area where it's not humid because the water in the air is going to absorb more of the signal than dry air would. The other thing people tend to overlook is that Wi-Fi is two-way communication. A lot of people go, yeah, but all I'm doing is streaming YouTube or Netflix. It's only one way from the AP to the phone, tablet, or whatever. And the answer is no, it's not. Because of using TCP, IP, which is one of the main protocols used on the internet, it's two-way communication. Basically, the AP sends some data to your phone, or whatever your client device may happen to be, and the client device says, hey, I got that data, everything came through, send the next batch. Or alternately, hey, we're missing some packets, I didn't get everything, please resend that to me. So even when you're doing something that feels like it's only one-way communication, there is always two-way communication going on. So a typical access point is around 500 milliwatts these days, maybe more, maybe over a watt of output power. But your iPhone is probably around 16 to 25 milliwatt. So a huge disparity in the power output. Also, the antennas are obviously bigger and more powerful on that affects it there. So what you run up into is a situation where your phone says, hey, I've got 4 bars of Wi-Fi power. You can't get Wi-Fi to work, or it's frustratingly bad, things keep timing out. And that's because the signal isn't getting back from your phone or mobile device back to the access point. So your phone's saying, hey, I've got a great signal because it's reporting what it hears. It doesn't know what your access point over here is hearing. So that's why you run into a lot of those issues, or you run into issues where you really should probably roam from one access point to another. and instead you stay stuck to that first one. That's part of what's going on there is the phone still thinks it's got a good, strong connection when it really doesn't. So RF, we use the term radio waves, and that is a very good analogy here. Is just talking about waves in water. Think about a pond, throw a rock in the pond and watch what the waves do. It's going to be very similar to what radio waves do. So in this case here, our transmitter, our access point or whatever, that's where the rock is plopped in the water. You see as the signal radiates out, if there's an obstruction in the way, it's going to lose strength. Now, in the case of radio waves, it can actually transmit through, just you're going to get a lot of attenuation versus water where you pretty much stop. You're going to get into situations here where some of the signal is going to wrap around. Some of the signal is going to miss the obstruction, going to hit a wall and reflect off of it. You can also get scattering where it reflects off slightly differently as it hits the wall. The wave hits in slightly different places along the wall, so it starts scattering the signal out. Exact same thing between. So one of the challenges we had with Wi-Fi is most of the protocol was defined back in the late 90s. Before we were streaming video, before we were doing a lot of networking stuff, and you didn't need a lot of bandwidth. The focus was just making it work. We weren't expecting to have a lot of devices sending a lot of data. So the solution they came up with, which was, how do I transmit data? How do I know it's safe to transmit data? So with radio waves, only one device can transmit at a time on the same frequency, with some exceptions that we'll get to later. Right, so how do you know that no one else is broadcasting so you can broadcast your data? And it's a really simple formula they came up with. Basically, you sense the medium, which means basically you listen. Is anybody else broadcasting? If nobody else is broadcasting, you go ahead and transmit what you need to transmit. If you hear somebody else transmitting, there's a little random number generated that determines how long you wait before repeating the process and checking again. And you just keep going through that until you don't hear anybody else transmitting. So it worked great in the days when we weren't doing a lot of stuff on the network. It causes tons of issues today because we have more devices that are trying to share the spectrum. In addition to Wi-Fi using 2.4 and 5, right? All sorts of other stuff. Bluetooth is using 2.4. The game controllers are using 2.4 or 5. The cordless phone is using 2.4 or 5. Remote control cars are using 2.4 or 5. So it's a very crowded space, and we're doing a lot more, right? We're not just occasionally downloading an email. We're making phone calls. We are, streaming 4K video over the internet. So we're using a lot more of the available airtime. So what's happening now is this is where your limit of how many client devices can get onto an access point. And we'll talk more about this later on in the webinar, but this is something that people need to understand is this is right here is one of the main limitations to how many devices you can have on your access point. Because we get that a lot. We'll go, well, this product says it supports 1.8, this product supports 512. The answer is in the real world, both are going to probably be limited to something like 32 or 64 or maybe even less, depending on what's going on because of this right here, because they're basically crowding each other. So not only do you have the problem where you might have, as you add more devices, two devices will listen, not see anybody else transmitting, and both decide to transmit at the same time, causing a collision, but you run into something here called the hidden node problem. Right, so you've got this access point in the middle of your office. One user is over here in the conference room on one side of the building. Another user is over here at his desk on the other side of the building. The access point can cover both of these, see and hear from both of them, but the individual client devices cannot see and hear each other. So you run into this problem a lot where both will listen, both won't hear anybody transmitting, or one will be transmitting, the other one will listen, and because they're so far away from each other, they won't hear them, so they'll decide, hey, it's okay for me to transmit too. So now you've got two devices transmitting at the same access point. Signals will cancel each other out or cause interference. You'll end up with a lot of dropped packets. Okay, moving on from there. Data rate versus throughput. Both of these terms are used interchangeably. There's some other terms that people use. But I want to highlight this and try to focus on this for our discussion. So I'm using the term data rate to be a measurement of the amount of data that's sent between 2 wireless devices as measured at the radio. So that is what you're going to see advertised as far as what Wi-Fi speed is whenever you're looking at a data sheet or a technical document. That's where it comes from. So that sometimes this is also referred to as a physical rate or a link rate, right? So with an N300 device, right, 300 megabits is the data rate, which is the maximum speed you can get. But then people will go and they'll run speedtest.net or they'll transfer a file over to NAS and say, hey, wait a minute, I'm only getting half that speed, or maybe not even half that speed. You guys are lying to us. And this has to do with just the way the IEEE works. IEEE is focused on data rate. People are focused more on throughput. And again, these terms can be used interchangeably depending on who's writing it. Just, to make it easier to understand, throughput is going to be what people are going to measure using something like speedtest.net, right? So what it is here is speedtest.net is measuring how much data you're sending from your web browser to a server out on the internet, or how much that server on the internet is sending back to you. So you're only seeing that data. What you're not seeing is protocol overhead. So in order to make Wi-Fi work in this crowded, noisy environment that anybody can be transmitting on, there's all sorts of protocol overhead that goes into making that work. And that protocol overhead easily takes up half of the available data rate as measured here. So basically, if you're sending 1 byte of data from your browser to a server on the internet, Wi-Fi is adding another bit of data on top of that, basically doubling how much data is being sent between your laptop, say, and your access point. So, that overhead can easily be up to 60% of the overall data rate. So you don't run into that with Ethernet. So Ethernet, there's a little bit of overhead, but not very much, so people don't notice it. But with something like Wi-Fi, where it can be 50 or 60% overhead, people get upset because they aren't seeing those speeds that are advertised, and that's why. And then, of course, there's other things there, right? Signal to noise ratio, strength noise, other things which may be degrading that signal and preventing you from even getting to that 300 data rate. Something just popped up here. Hold on. It's weird. Hold on. Sorry about that, guys. So we'll move from there. Hopefully that's been clear. So the next question is, how do we increase speed? And I'm coming at this from a technology standpoint, not a deployment standpoint. So as we've moved from 11A and B to 11G and N and AC and now AX or Wi-Fi 1 to 6, right, speeds keep getting faster. So how are we getting these faster speeds? One way we're doing that is by increasing the encoding. So that we use something called QAM. So 11N was 64 QAM, 11AC 256 QAM, and 11AX is 1024 QAM. It's basically the encoding we're using to cram more data onto the same amount of available spectrum. So that's one way we're increasing speed. The next way is by using multiple spatial streams. It's kind of a weird technology, so we've got a slide here coming up that goes a little bit more in depth to that. And then the other way to increase speed is by increasing the amount of bandwidth that any one device is using. So how much bandwidth, or how, I guess an analogy here might be, how large of a pipe you're using. A little tiny air hose versus like a fireman's hose, right? How much water can cram through at a time. So that's your bandwidth here. So 11G was 20 megahertz, 11N was 40 megahertz, 11AC gave us 80 megahertz, 11AC 2 gave us 160 megahertz. Let's talk a little bit about this, talk a little bit about channels and how that. So one of the challenges we have here on the 2.4 side of things, the 2.4 side of spectrum here in the US is about 60 megahertz in width. However, a Wi-Fi channel is around 20 megahertz in width. So even though when you go into the GUI, you will see 11 channels available to choose from, it's measuring at the center of the channel, and it's not counting what's on either side. And what happens is these gaps from 1, 2, 3, 4 on the channel numbers are not 20 megahertz spaced apart. So you get this huge amount of overlap. So again, you've got about 60 megahertz of spectrum here. Your Wi-Fi 2.4 is using at least 20. So that means you can only have 3 devices operating at a time without interfering with each other. So again, it's not just what's in your home, it's also what your neighbors are doing. Those signals from your neighbors can go really surprisingly far to cause interference. So like I was talking about, one of the ways we increase speed is we added 40 megahertz channels, which sounds great, right? The problem is you've only got 60 megahertz to play with and a 40 megahertz channel. So what happens is if you decide to start using 40 hertz of channel here, megahertz channel, I realize there's a typo there in the title. You can only have one device, right? As soon as you add a second device using 40 megahertz channels, you've got a huge amount of overlap and you've got interference. So this is one of those things where the advertised boost, right? We've doubled the bandwidth, so we've doubled our speed. As far as data sheets and product things or marketing is concerned, we've doubled the speed. Realistically, you're very rarely going to be able to use a 40 megahertz channel unless you live in a big house on a big lot. We don't have any neighbors with Wi-Fi. So part of the solution to that was the move to 5 gigahertz, right? We saw a little bit of this with 11N back in the day. It didn't really catch on until 11AC. So 5 gigahertz opens up a huge chunk of spectrum. I want to say there's like 26, 20 megahertz channels here to choose from. So you can have a lot more devices. This is why cordless phones pushed to 5 gigahertz. This is why Wi-Fi, starting with 11AC, made a really big push to move to 5 gigahertz because you've got a lot more spectrum to play with. But notice here, this big middle chunk here is highlighted and labeled DFS channel. So that's important. What is a DFS channel? So basically the FCC decided to open up 5 gigahertz for anybody to use. There was a problem, and that problem was people were already using this. People already had dedicated products using the spectrum, particularly radars, whether we're talking weather radar, military radar, airport radar, what have you. So what do you do with those radar users? Is you basically say, well, wait a minute, we get priority, Wi-Fi and these other, consumer uses do not. So what happens is something called DFS. So with DFS, basically, in order to use the 5 gigahertz spectrum, you choose your channel. Your device listens for, I think it's 20 to 30 seconds. And if it doesn't detect any radar or any of these other legacy uses, then it can start transmitting on the DFS channel. Now, if it detects a legacy thing like radar using that channel that it's on, it has to turn itself off and either change channels or just turn off for a period of time until it determines the channel is used. And if you're switching from one DFS channel to another DFS channel, you've got to again pause and listen before you can start transmitting. The other problem with DFS is it takes a lot longer to get Wi-Fi certified if you're using DFS channels versus not using DFS channels. So it can add up to 6 months to your FCC certification. So because of that, a lot of consumer equipment doesn't support these DFS channels, right? So a lot of equipment flat out isn't going to use these channels. So now you're only stuck with this green area here. So you've got like 9 non-overlapping channels if you want to DFS. So even if you're sure all your devices do support DFS, the other problem is you may get kicked off for a significant chunk of time if your access point determines that somebody else is using the spectrum that's a legacy user, such as radar. So you may get kicked off, and it takes a while to change those channels. So that's something else that people don't want to necessarily use these DFS channels, right? Especially if you're doing public Wi-Fi, you're doing a hotel. You don't want to explain to guests, well, you got kicked off for 40 seconds. Weather radar got turned on. So we had to change the channel, but we had to wait for the channel. So for a lot of users, don't want to channel. Now, the next thing you run into here, we're talking about we increase speed by increasing the channel width. We've got 9 non-overlapping channels. We want faster speeds, so we're going to use 40 megahertz channels. Now you've only got 4 non-overlapping channels that can be used simultaneously without interfering with each other. Of course, we want faster than that, right? So with 11AC, we came up with 80 megahertz channels. So now you're down to just 2 non-overlapping channels, right? So as soon as you add a third access point or a second neighbor, you're going to start having interference if you're all trying to use 80 megahertz channels. And then to get even faster speeds, right, with 11 AC Wave 2, we advertise speeds based on 160 megahertz channels. So there is no chunk of 5 gigahertz spectrum that's 160 megahertz wide that doesn't include DFS. So to support these modes, you must use these DFS channels. So that's it as far as channels and extra bandwidth. The next up is spatial stream. So with Wi-Fi, we talked about before, it behaves like a wave, bounces off of stuff. So what happens is we have something that's called multi-stream. So you're transmitting some data here. So that sort of out, right? Like a wave. Some of the signal reaches here first. Hey, Terry, I haven't touched my mic in forever, so I don't know what's going on. I'll let you know what. So maybe my mic's coming back. Sorry. But thanks for letting me know. I don't know what else I can do. I'll get it right now as close to my mouth as I can. Occasionally hitting it. So the signal radiates out. So you've got a straight line, right? Gets there the quickest. But the signal's also radiating out, hitting obstructions in the house or your office, right? Desks, people, cabinets, things like that. And then it bounces over and eventually gets here. So what happens is almost like an echo effect. You've got the same data, same signal being sent, and it's bouncing off of different things and all. So that's what we call multipath. So eventually some smart people, much smarter than myself, figured out ways to take this multipath problem and turn it into a benefit. And basically what it lets you do is it lets you transmit data simultaneously on the same channel, but different data without causing interference. Instead, it combines together. So what you can do is something advertised as MIMO, multiple in, multiple out. So it lets you send different data on each of your antennas, knowing that they're going to each follow a slightly different path. And then on the other hand here, you'll be able to receive both signals and combine them back together. So with 11N technology, we're talking about 150 megabits per spatial stream, right? So if you see an N300 product, it's telling you it's using 2 spatial streams, 200 spatial streams. If you had a product that was advertised as N450, it told you it was using 3 antennas, 3 spatial streams. So again, each antenna is sending different data, but it's using the exact same channel simultaneously. Because of this echo type effect, it makes it work without interfering with itself. It's really interesting. So the term spatial stream here is just referring to each different set of data that you're transmitting simultaneously. So one antenna is sending one spatial stream, the second antenna is sending a different spatial stream. There's a third antenna transmitting different data, that's a third spatial stream. So another technology came along with 11AC Wave 2, which is called MU-MIMO, multi-user MIMO. So instead of taking 2 different data streams like we had here and combining it together to one 300 megabits stream, we're taking those 2 spatial streams, each 150 megabits. Hey guys, thanks for the feedback on the audio. Unfortunately, there's nothing I can do to troubleshoot this later. So those that can hear me, so instead of combining this together to one 300 megabits connection, you can now send different streams of data simultaneously to multiple client devices. So you've got 150 megabit spatial stream going to one user, and a second simultaneous 150 megabit data stream going to a second user in this case. So when you're looking at data sheets, particularly on business class products, you will see normally the speeds measured not by an N300 or something like that, but on a business class product, you'll normally just see the spatial stream, 2 by 2, 3 by 3, whatever it happens to be. So the first number is telling you how many antennas are capable of transmitting different streams. The second number is telling you how many antennas are capable of receiving different streams. So in general, on access points, um, it'll match. So you'll have 3x3, 2x2, 4x4, whatever. However, on a lot of consumer products, particularly smaller mobile products, you may run up into a situation where you may see like a 1x2. You can receive two spatial streams simultaneously, but it can only transmit on one spatial stream. And if you're looking at particularly Cisco products, you'll see like a 4x4, then you'll see a colon and a smaller number. So that's a little something that Cisco does. So they're saying, hey, we've got 4 different antennas that can transmit, 4 different antennas that can receive, but we can actually only use 3 of them at a time. So you've got 4 to choose from, but you can only choose 3 of them at any one time. So it's really only 3 spatial streams, even though they're claiming 4 antennas. So Warren's asking, why would you do something like that? Part of it, I would argue, is just marketing, right? Trying to confuse things. Alternately, Cisco doesn't have smart antenna technology. It's something that we offer. It's something that Ruckus offers. So I think this is also kind of their way of trying to do something like smart antenna that's not really smart antenna. So in theory, right, you've got 4 antennas, but you can only use 3 at a time. So in some cases, three of them, are better than one of them, right? One of them's always the weak guy out as far as receive strength. So in theory, you could always make sure you're choosing the strongest 3 and giving you a little extra option there as far as which spatial stream you're going to pick up or which antenna you're using to pick up or transmit that spatial stream. I think real world scenario, it doesn't make really any difference. So I think it's more of a marketing thing these days. But it was actually fairly common back in the 11N days. But these days, I think I only normally see Cisco doing it. Tim was saying Cisco likes to make their own nomenclature to confuse IT people. So yeah, that is something. Cisco likes to take standards, modify and tweak the standard just a tiny bit, and then rebrand it as Cisco proprietary. Something you can do when you're the market share leader. Us small guys, we got to follow the standards. So to combine all those things together, we've got this little chart here, which combines all these different things. So this column is how many spatial streams you've got, your modulation type, and then your bandwidth that you're using. So we'll just take here a single spatial stream, right? Based on what we're doing here, we can get anywhere from a 390, or excuse me, anywhere from a 43.3 megabit data rate all the way up to almost a 900 megabit data rate, based on the type of QAM that's being used and the channel width. So a lot of this is going to be determined by your RF environment. Spatial streams are determined by your hardware. These other technologies are kind of determined by your hardware, right? Your hardware has to be able to support them, but these ones are affected heavily by your environment, right? So as I was talking about before, if there's interference on these channels, they'll normally drop back. So even though you might have it set to 160 megahertz, if you're in an office building, there's lots of other APs around, it will probably automatically fall back to an 80 or 40 megahertz channel just based on the environment. So we can see here using one spatial stream 16 QAM, right? We can go from 390 megabit data rate, all the way down to a 90 megabit data rate if we have to back off and start using a 40 megahertz channel. QAM also is heavily determined based on the data rate that you're using and on the signal to noise ratio. So if you've got bad signal to noise ratio, you may not be able to use 256 QAM. So again, we'll just use this scenario here. So if we have to drop from 256 to 64, our speed's going to drop from nearly 900 down to 650, assuming a 160 megahertz channel. So all of these things combine together to determine, what your current data rate is or your current speed is that you can achieve. So you're going to have different clients in your house connecting to different speeds based on their relationship to the access point and their relationship to other sources of interference. So as we talked about before, people always ask, well, how many devices can I put on your AP? Your data sheet says you support 512. I've only got 30 users. Why am I having Wi-Fi issues? You guys lied to me. So when you're looking at data sheets, you know, the number of client devices that can be supported is basically just a measurement of how much memory is allocated to the association table. Right? How many MAC addresses can it keep track of? You know, realistically though, how many users is determined by the protocol, and you're going to hit the protocol limits. Right? We talked a little bit about that before about how you had more devices and more likely to connect at the same time. So what you're doing is affect things a lot. See the data sheet. So it really doesn't matter if you're using a $50 product, $700 business class product. The number of users, assuming they're the same Wi-Fi technology, is going to be pretty much the same in the real world because it's the Wi-Fi spec itself, which is where you're going to start hitting limitations. So here's one example, many different types of examples. This is a simplified one. We're taking a simulated scenario here. Basically, we've got 3 different types of wireless device, all with the same signal strength, all with the same, basically everything. And they're trying to stream a 3 megabit per second video stream. So it's a, you know, like a 720p YouTube stream or maybe even 1080 these days. They may compress them that much. So if you've got a laptop that supports 3 spatial streams and an access point, you can have 34 users simultaneously for streaming a 3 megabit stream without any issues. As soon as you add the 35th, you'll start having issues. So if we just change the device and remove one of those spatial streams and make it 2 spatial streams, now you can only fit 21 on there. Again, nothing's changed on the access point. And the reason for that is you're utilizing the airtime less because you can only transmit 2 spatial streams at a time. So now we're down to 21. If we reduce this to 1 spatial stream, now you've only got 10 devices that can stream that 3 megabit video stream simultaneously before you start running into issues. So this is one of the big challenges you run into here when determining how many users you can fit on there is it's really heavily dependent. So in this case, we were simply looking at spatial streams, but this is going to be affected by the data rate, by the channel bandwidth that they can support, their signal to noise ratio. So it becomes a real mess. Also, different types of data, right, are going to affect things. So in this case, we were talking about a 3 megabit stream. One of the hardest streams to deal with is a VoIP stream, and maybe why we're having audio issues today, right? Because when you're doing audio, specifically a conference call or something like that, it's two-way real-time. If you're streaming something from Netflix or YouTube, you're not watching that in real time. It's a little bit of a delay. So if some of those packets get dropped or come in, it's not a big deal. But when you're doing a voice call, it becomes a big deal because you can't buffer much of that signal, right? Because then you end up talking over each other because there's too much of what you're saying. So because of that, even though it's highly sensitive to sort of delays and packets or drop packets, sound quality. So let's move on from there here. We're talking a little bit about co-channel interference. So again, co-channel interference is just basically 2 or more devices broadcasting at the same time on the same channel, which causes error. Right, so it can be other access points, other cordless or wireless devices. It can be a microwave. A microwave uses the 2 space. If you are, you know, in a business environment, most business electrical equipment doesn't comply with FCC Class B regulations as far as RF. So you end up with a lot of stuff putting out RF. Unless you have an RF meter and you're walking around, you wouldn't realize that, say, your air conditioner is putting out a ton of RF using the at 5 gigahertz, which may be causing interference, et cetera. So the way we deal with that generally, historically, has been, right, we plan out where each access point is going. We carefully make sure they're not using overlapping channels as best we can. And then if we're still having issues, then we turn down the power on our access points. So the power on the access points is much closer to what the mobile devices are using, right? So instead of having 500 milliwatt access point connecting to a 25 milliwatt tablet, maybe we drop the power here to 100 milliwatts or 50 milliwatts to make them more evenly match, which is great. It reduces your co-channel interference between these two different APs, but it lowers your signal to noise ratio because the signal's less. So you end up with a lower data rate. You may end up with just as bad, if not worse, Wi-Fi issues. So the solution we have is something called smart antenna. So traditionally, your typical ceiling access point um, is designed to cover a circular area here. So you've got a sort of a round coverage pattern. The exception being if you're doing that like an outdoor point-to-point antenna, it's got a focused antenna. So smart antenna changes things here, but instead of having this one, you actually can use literally hundreds of different antenna. So we've got an algorithm that basically takes a look at where the client device you're trying to transmit is in relation to the access point, and also any other sources of interference, whether Wi-Fi devices, other sources of interference there, and we choose out of these hundreds of antenna patterns the appropriate pattern to A, focus the beam on the client, but also try to reduce where we're listening to reduce hearing those other sources of interference. Now, this doesn't require anything special be done on the client, unlike beamforming, and it also works with moving devices. So it allows you to basically in real time keep adjusting which antenna pattern it's using for each client. It makes a huge difference in performance. So here's an example here. This is using a hotel environment. This is using in-room access points. As you can see, we've got the 5 gigahertz channels spaced out nicely next to each other. In this case here, you've only got on this floor one AP using the 100 channel 100, and then the other two APs are on a second floor. So for this test, we took our product and we took a Ubiquiti product. The products on paper are basically the same spec. Big difference being the fact we've got smart antenna and Ubiquiti doesn't. So we turn on one access point, connect a couple clients to it, and see what the aggregated throughput is. So you can see here with just one AP turned on, smart antenna makes no difference. Right, both of them are getting basically the same speed. In fact, Ubiquiti beats us. Both are getting essentially identical airtime utilization. Now, what happens when we turn on a second access point? Again, they're not next to each other. They're on a different floor. What you see now is the aggregated throughput between both of those APs and their clients is 785 with the smart antenna. But on Ubiquiti, it's only 555 megabits per second. So a big performance boost from the smart antenna. So why is that? It has to do with the airtime utilization or channel efficiency. So Ubiquiti is getting up to 95% airtime utilization, right, of the theoretical 100% max. Zycel, on the other hand, has exceeded the theoretical maximum, and we're getting up to 131% efficiency. So how is that possible? It's because with the smart antenna, some of that data that would be causing interference over here allows us to have multiple devices transmitting at the same time without interfering with each other. So now what happens if we add a third access point and turn it on? What we see here is Ubiquiti's airtime utilization actually goes down from 95 to 91, just because you've got more people stepping on each other's toes. As we talked about before, airtime utilization is, the algorithm is really simple. Listen if anyone else is transmitting. If they're not if someone is transmitting, back off a random amount of time. Whereas our channel efficiency has gone up from 130% of the theoretical maximum up to 155. So aggregated throughput here is over 900, where aggregated throughput on Ubiquiti basically didn't go up at all. The other important thing to note here is look at how the data rates are aggregated between these access points. Notice with the smart antenna, each access point is getting basically the same amount of aggregated throughput. With Ubiquiti, it's all over the place because they're basically fighting with each other. Whereas with smart antenna, they're ignoring each So it makes a huge difference in environments where you've got lots of client devices connecting to an AP. You've got a lot of APs crammed into the same area. So it makes a huge difference in hotels, condo buildings, apartments. Makes a big difference in expo centers or conference. So I'm going to hit some of the questions here. The first question was from Warren, who's asking, how are there any actual network cards that use three channels at a time? So again, it's not channels, it's spatial streams. So a device is only using one channel at a time. It can use multiple spatial streams. Yes, there are. There are definitely products out there that support three spatial streams. Like I said, on a lot of stuff, especially the cheaper stuff, it's really common to see like a 1x2 or a 2x3. But you can get USB adapters that do 3x3 or 4x4. They are out there. There's probably embedded devices that do 3x3 and 4x4. I can't think of any off the top of my head, but it's not something I normally pay a lot of attention to. So how do we figure out how many spatial streams a network device supports? So that's another good question here from Warren. In the case of access points and most business class products, it will be on the data sheet, right? So we don't, it'll be 3x3, 2x2. You will find that on the specs. For client devices, it's harder. In fact, a lot of times it's really, really hard to find any detailed specs on consumer type devices. You know, I was trying to figure out these days with current the new iPhone, you know, how many spatial streams it supports, how many channels it supports, things like that. We don't publish that anywhere. You're basically stuck waiting for somebody else to do a teardown, figure out the chip, and chip chip data sheet supports. Um, Sometimes you can get lucky if they'll advertise the speed. For instance, again, if it's an N product, they may advertise that it's an N300. So then you know it supports two spatial streams because the maximum speed of an N spatial stream is 50. And you can do the math, like if it's an AC product and you say it's, you know, an AC 2600, you can do the math and try to figure that out. It gets more tricky on these newer devices because they are, right, dual radio. You've got a 2.4 and a 5 gigahertz radio. At least on the AP and router side of things, they combine two radios together. Client devices sometimes combine them together, sometimes don't. It just depends on about the data sheet or the specs. So it can be hard on the client side of things. Warren's also asking here, is smart antenna a 2D or 3D shape? So it's a 3D antenna pattern. So it goes through hundreds and hundreds of different antenna patterns for all different types of environments. Tim's got a question here. Are there wireless APs that require FCC or technician license? So when it comes to Wi-Fi, true Wi-Fi products, we are all operating in unlicensed spectrum. So there is no licenses required. As you start getting into, as you mentioned there, those tend to start using licensed spectrum, or in the case of 60 gigahertz, it's not really licensed, but it's more heavily monitored. So those may require additional certification or a channel license to be able to use those. But I've never heard of it with an actual true Wi-Fi product, but I have seen stuff like that with products that are based on Wi-Fi but aren't actually following the Wi-Fi standard. Okay, back to the slides. Now that we've gotten kind of caught up. So again, what I was talking about before, an access point is designed basically to be mounted to a ceiling, and it's generally got this round antenna coverage pattern. But in the real world, right, a lot of times your customer won't let you mount it to the ceiling. There's no ceiling. So you end up having to mount it on the wall. And so you get a less than ideal coverage pattern. Now, one way that Zycel solves this obviously is the smart antenna products. We also have products that have what we call dual optimized antennas. So they've got two different sets of antennas, one optimized for ceiling, one optimized for wall mount. And you can choose which to use based on where you mount the device. That's one way of helping solve those issues that Zycel offers. But generally, the rules here when you're mounting your products is mount them on the ceiling if you can. Mounting them on the wall will reduce coverage, and if you're in a multi-floor building, may end up sending signal upstairs and downstairs and causing interference. Generally, the higher you mount the access point, the better. You're basically trying to remove as many obstructions as you can from blocking the signal. So within reason, right? If you're doing this inside the probably wouldn't want to mount 10 feet. It's too high up. But generally, in most businesses, you'll try to mount it as high as go on the drop ceiling or maybe drop ceiling. So one thing we run into a lot is people say, well, my customer doesn't want me to mount it on the drop ceiling. Or cold in the drop ceiling and heavy. You know what? That's fine. Just lay it on top of the drop ceiling. Um, it's generally going to be up the building code that way. Um, but the standard acoustic tiles have very little signal attenuation. It doesn't really matter if it's hanging down from the ceiling or you're just resting it on top of the ceiling. You want to make sure you do it the right way. The slide has it should be. Um, if you are mounting it on the actual ceiling above the drop ceiling, keep in mind that generally that real ceiling is filled with all sorts of metal stuff. It's probably pretty bad for air, right? You've got ductwork, insulation with metal back. You've got pipes, you've got sprinklers, you've got the wires that hold the drop ceiling up. So all of that metal stuff is going to block or reflect the signal. So generally, you want to try to avoid mounting it on the ceiling if you've got a bunch of other stuff up there. So for hotels, the traditional way of doing hotels was, so Terry's asking here, wouldn't devices in the ceiling violate code? Are the devices certified to work in plenum space? Yeah, most access points are plenum rated. So just check the data sheet. The data sheet will generally say if the device is plenum rated. A lot of access points are plenum rated, so they're safe. And in some cases, in some building codes, depending on where you are, you don't even need to be plenum rated, just because these are operating off of DC power. So they're operating on less than 15 watts of DC power. So in some places, you don't have to be plenum rated for low voltage devices like that because there's very little risk of them catching fire. But it varies quite a bit based on where you happen to be at. So anyways, back to hotels. The traditional way of doing hotel coverage was you would mount the AP in the hallway, and you would cover anywhere from 4 to 16 rooms with one access point. It was cheap. You didn't have to run a lot of cables. You didn't have to run a lot of access points. And it worked great. And most users who were connecting to Wi-Fi were business users who were connecting a single laptop and downloading email periodically. Doesn't cut it these days where you've got, between mom, dad, and a couple of kids, you may have 6 different devices on there. Everyone's wanting to stream video or do a live stream themselves upstream. It just doesn't work. So what you're seeing these days is most hotels are moving to 1 AP per room or 1 AP per every other room. And there's a number of different access points out there that are specifically designed for this type of environment. They generally also have Ethernet pass-through, sometimes PoE pass-through. So you can run 1 Ethernet cable to the room, power your access point, power a VoIP phone in the room, run video to your IP set-top box or IPTV that's being used in the room. So this is where the trend is moving as far as in-room coverage goes. Another thing to look at if you're mounting in-room is you want something that's going to lock, or at least have it difficult for people to figure out how to unlock it from the wall, because otherwise people will steal these. Another thing to take into account if you're mounting them in the room is have the ability to turn off the LEDs. A lot of guests are going to have issues sleeping if they're laying in bed looking up at a green, orange, flashing light all night. In public areas, basically what you want to generally take into consideration is user density. How many users are actually going to be on? And use that to determine how many APs you cover that area. Generally, you want to plan your Wi-Fi deployment based on the individual area. So even if the restaurant is right off the lobby, you have a separate restaurant network versus your lobby. To plan each area independently and generally view each other. You want to use load balancing and client steering to help avoid AP overload. And again, in any area where you've got a lot of APs in the same area or a lot of users in the same area, smart antenna makes a world of difference. So when it comes to schools, It really depends on what's going on in the room. Is this a smart classroom where every student has a Chromebook or a tablet that is always on the network? Or is it a room where maybe kids just get online every now and then to study? Is this a situation where the teacher is broadcasting their screen or video content to every student's laptop, or is the students just using it to browse the internet, maybe do some homework type stuff? So, basically, how much are they actually utilizing the Wi-Fi network? And that takes you to where you're kind of looking at things. In general, a teacher and students should be viewing off of each other, right? You don't want the students hacking into the teacher's PC, but you need to have some rules in place set up so the teacher, when they're streaming, can push stuff out across the network. Generally, use 2 APs per classroom. If you're 20 students or more, if you're at 30 students or more in the room, be smart into that. All of our Wi-Fi devices, whether they're controller managed or Nebula Cloud managed, we have a special smart classroom algorithm, load balancing, that's specifically designed for these classrooms where you may have 5 students coming in and connecting. So now we'll talk a little bit about 802.11ax, aka Wi-Fi 6, and at one point it was being advertised as high efficiency wireless. But all three of these things are the same thing. 802.11ax is the IEEE spec that's defined it. Wi-Fi 6 is the branding that the Wi-Fi Alliance has given it. So something interesting here is Wi-Fi 6 was designed to work on any frequency. So 11AC only brought benefits to the 5 gigahertz radio. An 11AC access pointer product, the 2.4 radio is still using 11N or Wi-Fi 4 technology. So with Wi-Fi 6, both radios can be using and taking advantage of all the changes made to Wi-Fi 6. It was specifically, it's almost a complete roundup rewrite of Wi-Fi to solve all of the issues that we have had with Wi-Fi. So there's a bunch of different technologies that go for users on the same access point. More access points in the same area without interfering with each other. Um, being able to time and coordinate with the users to more efficiently use the available airtime rather than relying on individual clients to sort of listen and guess when it's okay for them to transmit. All sorts of cool stuff that we are doing now that solves a ton of issues. It adds the ability to do uplink MU-MIMO. So remember before we were talking about MU-MIMO with Wave 2, it allowed the AP to transmit data simultaneously to multiple clients. Uplink MU-MIMO, now we can send data from multiple clients to the access point simultaneously. We've got the ability to read the spectrum. We've got the ability to chunk up the spectrum into really tiny little pieces and properly allocate the spectrum based on each individual client device's capability of using the spectrum. All sorts of things. So, Wi-Fi Alliance has been certifying Wi-Fi 6. It has just begun there. It started last fall. However, this is interesting, right? So you can get Wi-Fi 6 certified. However, the actual IEEE standard still is not been finalized. We're hoping right now that the work group will vote for approval here in Q4. And final approval, they're hoping for Q1 next year, but this keeps slipping. So who knows when the actual final spec will come. So a little bit of mishmash there. The other interesting thing is people have been selling Wi-Fi 6 products since 2018, right? And we still don't have a final spec. So how is that possible? So first important key thing here is a lot of the first generations of Wi-Fi 6 products don't support a bunch of the different parts of what makes Wi-Fi 6 Wi-Fi 6. You may not support OFDM. You may only support downlink OFDM. You may not support uplink MU-MIMO. You may not embed BSS color coding. All these different technologies because the silicon wasn't ready and the spec wasn't ready. So that leads us to this slide, which is when Wi-Fi 6 isn't Wi-Fi 6. So a lot of products that were rushed to market, especially on the consumer side of things, are using these early generation chipsets. On my chart here, I've got Qualcomm. Broadcom is very similar to this. And those are the two main chipsets that are making Wi-Fi 6 products. So both of them had a first gen chipsets, 1.1, 1.2, et cetera. and they are missing out on key features. So in the consumer side of things, we've seen this over and over again. Consumer is all about being first to market with a new tech, getting mind share and things like that. And there's very little thought put on, reliability, standards compliance, things like that. So that's why you see stuff hitting consumer markets generally first. But even on the business side of things, Cisco, um, Edimax, a number of other vendors out there have launched Wi-Fi 6 business class products, but they're using these Gen 1 chips that are missing some of the key features that make Wi-Fi 6 so different from Wi-Fi 5 and the other previous stuff on there. So basically, these Gen 2 chips didn't start shipping until um, late summer, early fall last year. So if the product launched before early fall last year, it's probably or for a fact it's a Gen 1 chipset, and it's not truly Wi-Fi 6. But even today, stuff that's coming out may not be using a Gen 2 chip, right? The Gen 1 chips are still there and they're cheaper. So you may see people advertising a Wi-Fi 6 product that doesn't support all of the really important features that are part of Wi-Fi 6. So for Zycel, all of our Wi-Fi 6 products, whether consumer or business, are using Gen 2 chips. They support all the key features, and whenever the IEEE standard finally gets ratified, there'll be a firmware update if there's any tweaks that are needed. So they should be able to support whatever the final standard is. It's far enough along that there's not going to be any major changes. Another thing you're going to see out there, Ubiquiti is an example of this, is their Wi-Fi 6 product. They're only rolling out Wi-Fi 6 on the 5 gigahertz radio. The 2.4 radio is still using Wi-Fi 4 technology, even though Wi-Fi 6 is designed to work on both radios. So that's something else to keep in mind. And so obviously a lot of these vendors aren't advertising the fact, hey, partial Wi-Fi 6 features, hey, Wi-Fi 6, but only on one of the two radios. So you've got to kind of pay attention to the data sheet and look, are they mentioning OFDMA? Are they mentioning TWT? Are they mentioning upstream MIMO? If they're not, they're probably using a Gen 1 chip, and look at the data rates that they're claiming on both radios. If they're only claiming claiming 300 megabits or 450 megabits on the 2.4 radio, it's using 11N technology. There's also something new called Wi-Fi 6E. So the FCC, late spring, early summer, opened up a good chunk of the 6 gigahertz spectrum for unlicensed use. So products that use this are going to be advertised as Wi-Fi 6E. So the E stands for extended. It's going to be fantastic for speed because you've got 7 non-overlapping 160 megahertz channels, right? So this is fantastic for condos and apartments and office buildings where you've got a lot of APs. You can get maximum bandwidth utilization with very little chance of interference from other access points if you've planned it out properly. So what is the catch? So the catches here are kind of a couple different things here. The first one is, again, remember, as frequency goes up, range goes down. So these 6 gigahertz channels are going to have even less range than 5 gigahertz does now. The other problem you're running into is just like with 5 gigahertz, this spectrum is already being used by people. So there's a technology that has to be adopted similar to DFS called AFC, automated. So basically, similar to DFS, you have to check if one of these other legacy users is operating on the channel you want to use in the channel. I'm not going to get into it. There's some pitches are similar. But expect this to be big, right? 7 non-overlapping 400 to 5 gigahertz. So it's going to be. So right now, as far as I'm up to date on, only the U.S. has approved it, is expected to do this, but not as big of a chunk of the spectrum. But I don't think in general the EU is really power output and things like that. But eventually, this will probably spread around. So Wi-Fi Alliance is expected to start certifying this stuff in 2021. I know ASUS and I think a couple of the other consumer vendors have already announced product, although I don't think shipping it. But again, it's not going to do you any good until you've also got a client device. So until your iPhone or your tablet or it's not going to do you any. PlayStation doesn't support 60 blocks. So it's going to be a while before devices support 6E. Still, it's going to be a long while before regular Wi-Fi 6 is. So something to keep in mind. So with that, that's it, guys. That is today's webinar. Thank you for tuning out. Sorry about those audio issues. I'm not sure if it's the mic or the internet or if it's Wi-Fi. I don't know what's going on. It's the first time I've done about that. I'm not sure the cause. If you have any questions, though, send them in on the Q&A window. Also, my email is up there on the screen, seanr@zycel.com. Feel free to ask me questions offline. Give me suggestions for other topics you'd like to cover. Let me know what sucked about today's presentation and how we could have made it better for you. I love feedback. I love constructive criticism. And then also, I just want to draw your attention here that we do have user forums available at forum.zycel.com. There's both a consumer and a business user forum. And unlike most vendors' user forums, where it's pretty much just the users talking to each other, our R&D see your feedback, and oftentimes they do chime in and answer questions. So if you've got an issue that you're having that doesn't need tech support and can take a while, it might be a good idea to post it there. Feedback, suggestions on product features, usability, things like that. It's a great place to post it. So our HQ can see that feedback, and you can also see if other users are agreeing with you to help prioritize things. Frank Adams is asking, is this available online? I'm not sure what that's directed to. Today's webinar is being recorded. It will be published to our YouTube channel. And this is not my first time I've done Wi-Fi 101. So if the audio sucks on the recording as well, maybe watch one of the previous months. Wi-Fi 101, I cover most of the same slides. So if this recording has audio issues, maybe the previous one doesn't for you. Carmine is asking, why is the signal to noise ratio displayed as a negative number? Receive sensitivity or receive strength is always measured as a negative. Once upon a time, I knew the engineering for that, and I am drawing a blank right at the moment. So apologies that I don't have the explanation for that, but I do know that's pretty standard in how things are done. Receive sensitivity, signal strength of a connection is always measured as a negative. I forget the reason why. Sorry. I am not seeing any other questions coming in. I'll hang out here for a few more seconds, see if anything else comes in. But again, feel free to just email me offline. I thank you guys for turning out. Please join some more other webinars that are coming up. Every month we do a new partner introduction where we do a high-level overview of all of the different products that we've got. So if you're new to Zycel, we've got over 300 different SKUs, so that's a good webinar to go to just get an idea of what other stuff we've got that may be of interest to you. Try's doing a bunch of different webinars, particularly around security products. I've got another Wi-Fi 6 webinar coming up. We're constantly doing webinars on our Nebula cloud management solution. It's a great way to reduce the amount of time you have to spend on customer premise. So you don't have to worry about your techs being worried about COVID. You don't have to worry about your customers worried about strangers being in their home or building. Makes it really easy to do remote management reporting, to offer MSP type services. So if you haven't played with it yet, join that. But we don't have any other questions. So again, thank you guys for joining us. Go ahead and end today's webinar. Question that comes up.